Hi there and welcome to Calculus of Variations. In this video we're going to look at the shortest distance between 2 points. We're going to show it's a straight line, but we're going to do it in polar coordinates. Now let's consider the polar form of a straight line. So if I draw a straight line in here, so I get it from here, there we go, a straight line. And if I were to draw in a couple of coordinate axes, let's just draw from here. Okay, and I'll just undo that. Okay, got that. Okay, so we'll just call these our X and our Y axis. Okay, now we're looking for the polar form of this. Now let's imagine we have our distance here from there to there. Okay, we'll call that R. Okay, so now in polar form, R is going to sweep through some angle of, let's call it theta. Okay, so this R is going to sweep through an angle of theta and make out a circle. Now let's take this line here and we'll drop a perpendicular to the origin. Okay, so say we drop perpendicular to the origin there. Okay, and we'll then look at a point up here. So we'll have a distance there, and we'll make this distance here equal to a distance there, which we'll draw up here. Okay, so I'll just pop it there. Okay, so we call this, that's going to be a right angle. Okay, and we'll call this length here, we'll call that C. We'll call this angle here alpha, and we'll call the whole angle, big angle around here, we'll call the big angle theta. Then this angle in here, from here to here, is going to be theta minus alpha. I'll just pop it there. So that's going to be theta minus alpha. Okay, now this point up here, remember this length here is just going to be R as well. This point up here we'll call P, and the polar coordinates for that point will be P R theta. Then we can see that this distance here, C upon R, is the cosine of this angle here. So we could say that C upon R equals cos of theta minus alpha, or equally we could say C equals R cos theta minus alpha. Okay, so that there is a polar coordinate of a straight line. Now we want to do the same, we want to find this same expression, but we want to find the same expression using calculus of variations. Now let's draw in another set of coordinate axes. I'll just draw that. Okay. Here again that's our X and that's our Y. Then if we were to draw a curve, okay, should actually, before I do that, what I'll do is I'll take those out. Okay, you'll see why in a minute. Right, now if we were to draw a curve, right, so I'll just pick some curve, there we go. I'll fix my colours here first. Right, if we were to draw a curve, so there you go, some random curve, and I was to take a small element of that curve there, okay, and I was to blow it up, and I said what's the length of that element of the curve, so that would be some element there of the curve, okay, and there would be a value here, right, and if I drop the perpendicular, a value there, so we could make a small triangle out of this. Now what we could do is we could look at the tangent to the curve, okay, so we could just draw a tangent in, so there's a tangent to the curve there, okay, there's a tangent there, and from that we could draw in our axis system from this point here, say, so well, I'll actually run it all the way down, okay, so from there to there, and that direction as well, okay, I'll just continue that down, so that there feeds all the way up, and I'll continue this up as well, just so you can get the triangle. So that there is just an extension, that's the tangent of the curve at that point, so this would be this distance here. Now if we call this distance here r to this point, okay, then the extra distance added on here, we could call that, now we'll call that dr. Now I know dr is meant to be a small element, but obviously I'm just trying to draw it out here, so I have to make it larger, don't I? So we could call that dr, okay, and we know that this side here is ds. Now if we were to drop that perpendicular there over to the curve, we could draw another line up here from this point up to that point, okay. Now that again is some distance r, okay, and that's a distance r, and see this little curve here, that's one segment of the arc that this line here will make as it sweeps along in a large circle. Now that little segment of arc there is going to be r times theta. Now, so that means that this distance here would be, if it was r, and if theta was very small, it would be r d theta. Now you can see that's r theta, because if you had a, say, circumference of a circle, c equals 2 pi times r. Now we know that circumference of a circle, if this value here is just your value for your r, and the 2 theta, well that's just some number in radians, and the number in radians here will be given by theta, okay. So now this distance here is a straight line and that's a curve, but as that value of dr gets smaller and smaller, so there's dr getting smaller and smaller, say we take dr to be this distance here, then and the limit as dr tends to 0, this line here tends towards the length of that curve there, okay. So that's just an intuitive description of what's happening. So we can say that this distance here approximately equals r theta, okay. Now, so we've got a little triangle here, and we can redraw it, or rather we don't need to redraw it, we can see what it is. What we can say is we can say that ds squared equals dr squared plus r d theta squared. Now there's two ways we can look at this in calculus of variations. We could look at it in terms of ds squared upon dr squared, or we could look at it in terms of ds squared upon d theta squared. Both are equally valid. Okay, so the question is which one do we choose? And well, let's work through and we'll work out a logic for choosing one of them. We could rewrite that there as, well, we'll define that throughout by dr squared, so that would be 1 plus, and we would have r squared, okay, and r squared by dr. Oh, would be, I'm going to write that again, get it right this time. Okay, so we would have dr squared, and then we would have r squared, okay, for the squared term here, and then we would have d theta upon dr. Okay, all squared. So then we could take up the dr, and we can take the dr squared, and we could take the root of everything. So we would end up with ds would equal 1 plus r squared, and we just call that theta derivative squared, and it would all be to the power of a half, okay, times dr. Okay, that's one way of writing it. The other way is to divide through it by d theta squared, so you'd end up with r squared plus dr squared upon d theta squared, and again ds would equal r squared plus r derivative squared power of a half times d theta. Now which one to use, 1 or 2? Well, in number 1 we would have, if we were to write it out in a functional format, I would equal the integral from a to b of some function, okay, and the independent variable would be r, okay, and r would be dependent on this value of theta derivative squared would be our an explicit value within the functional. Okay, so we would have theta derivative by dr. Okay, so that's the first one. And the second one, we would have I would equal the integral from a to b of f of, now the independent variable here would be theta, okay, and it would have an explicit dependence, but it's going to have an explicit dependence on r and an explicit dependence on r derivative. Okay, so now we know that we can use a simplified version of Euler-Lagrange, which would really say partial f upon, now in this instance here we would have partial theta derivative would equal a constant, so we could use that because there's no explicit dependence on theta. So we could use that for number 1, but we couldn't use that for number 2. We would have to use the full Euler-Lagrange in order to find the value in example 2. Okay, so we don't want to use that, but we want to use that one there. Okay, so I just went through that just so you could see the Euler-Lagrange written with different variables and just get used to seeing it. So let's go ahead and we'll do the calculus of variations in this. So if we said I equals the integral from a to b of, and it's the first one, so it's 1 plus r squared theta derivative squared to the power of a half. So 1 plus r squared theta derivative squared all to the power of a half dr, and we're looking to, I'll just write it out, so what we're going to find, we're looking for partial by partial theta of the 1 plus r squared theta derivative squared to the power of a half. Okay, so we can do that quite quickly. Again, we've seen it in other ones. It's a function of a function, so it's that becomes a half to the minus a half, and then we're differentiate with respect to theta derivative, so that would become 2 r squared theta derivative, so, and that would equal a constant, so you're going to end up with r squared theta derivative upon 1 plus r squared theta derivative squared all to the power of a half equals a constant. Now, really that's what we've done our calculus of variations bit. I mean that's our the value that we've ended up with, but the rest of it is really manipulation and trying to get it back into this form here. Okay, so we'll just work through that manipulation. So now what we want to do is we want to solve for theta derivative squared. Now I'm not going to work through this full solution here because it's just algebra. What we were going to have to do is we could take this whole line up here, multiply it by c, we could square this and then square all that to get rid of the power of a half, and then we can take our factor of theta derivative back over to this side here, and then we could make theta derivative the subject of the equation. So you could just work through that yourselves, it's quite straightforward. So you would end up with theta derivative squared equals c squared upon r to the 4 minus r squared c squared. Okay, so then we could write theta derivative would equal the root of c squared upon r to the 4 minus r squared c squared. Okay, that could be rewritten as theta derivative equals, well, the root of c squared, that's going to be our value for c, and we can write that as r squared minus c squared, just take the r squared out of that, and we want to find the root of that. Okay, and then we could rewrite this here because it's going to be d theta by dr equals c upon, now what we'll do is we'll take the r squared out of the square root, so you're going to end up with r root r squared minus c squared. Now what you could do is multiply both ends by dr and multiply by 1 upon d theta. So really what you're doing is you're just taking the dr up and the d theta down. Okay, so you'll have 1 equals c upon r root r squared minus c squared times dr by d theta. Okay, so then you could then say, if you take the d theta up here, you'd have the integral of d theta equals the integral of c upon, now another little trick, we can take out another factor of r out of this root term, so you could end up with r squared root 1 minus c upon r all squared by dr. Okay, now I can maybe put a box around that. Okay, now what we want to do is get this side here into a standard form. Now the standard form that, I'll just write that, a standard form, okay, for integration. Now the standard form we're going to use is integral minus 1 upon root of a squared minus x squared by dx. Okay, so there's the x there, c upon r. Now the dx here, well, I've got dr there, so we need to do something with that, and we've got a factor of c, we've got a factor of r squared, and there's no negative sign in it, so it's not quite right in the right format. So what we can do is we can use a substitution. Okay, now I'll try and get it in here actually before I go on to a different page. If we note that if I take the d by dr of c upon r, okay, that's going to give me minus c upon r squared. Okay, now I can take the dr up here. Okay, so I'll just scrub that out. So now take the dr up. Okay, so I would have dr. Okay, now that's the substitution that we are going to make. Okay, so we can replace this c upon r squared dr. Okay, we can replace that with minus dc upon r. Now we have to replace it by the minus because we end up with a minus sign coming in here. Okay, and we need to get back to a positive there, so we need to do it with respect to a minus d upon cr. Okay, so when we do that replacement there, if you're not sure about that, just check up integration by substitution. Okay, so we would end up with an integral of d theta equals the integral of minus 1 upon root 1 minus c upon r squared, and we're differentiating it with respect to c upon r. Okay, so now we've got that there in exactly that standard form that we were looking for here. Okay, the a is the 1, the x is the c upon r, and the dx we've got dc upon r, and there's a negative sign in there as well. Now that there, I've never even finished this standard form, that is actually equal to inverse cos x upon a. Okay, I'll try and draw a box around that there. Okay, so that would be the standard form that we're going to use. So we can then take this thing here and we can say that cos, inverse cos, right, and it's going to be x, which is c upon r, upon a, which is 1, so it's just going to be c upon r equals, now when we differentiate that you're going to have theta and a plus some value which is a constant of integration. Now we're actually going to write it as theta minus alpha in order to get it in the same format that we have up here. Okay, now it could be theta plus alpha, but alpha might be a negative number, so theta plus a negative number. Okay, so we can use theta minus alpha if we want. Okay, so we end up with that there, and I think I can just squeeze this in here. So we would end up with, that's the inverse cos, so if we want to get the cos of that, that would be equal to cos of theta minus alpha equals c upon r. So we can then say, and I've just managed to squeeze this in the very last little bit of the line, which is good, c equals r cos theta minus alpha, which was our original equation for polar equation of a straight line. Okay, so that is equal to the equation there we wanted to get. Thank you for listening, and I'll go and I'll do another example. And you notice in a lot of these examples there's about 1/10 of it is actual calculus of variations, the other 9/10 is just known standard calculus and manipulating it. Okay, thank you and goodbye.